Okay, let's start. Yeah, so just I will start with one correction. It's not correction, one clarification. So last time we were discussing this uh, probability PDF and CDF associated with a normal distribution, right? So uh, I think I was at some point I was saying that uh, the point at which or up to which that we were calculating probability. That might be confusing what I said if you are listening to the video, the structure of my sentence that may make some confusion. So let me clarify that. Let's I will ask a fundamental question. Let's say you have a PDF like this, a Gaussian PDF. So this is the random variable here. So what is the probability that the random variable x take value? Let's say this point is x. Okay. What is this probability? So this is my.
I don't know the exact word, but it is basically 0.
Okay. Yeah, that's correct. Right. So
yeah,
it is 0 actually. Okay. So because you are this is a continuous distribution, right?
Yeah.
If it was a discrete distribution, you can pick that value from the PDF. But here
there's a limit to 0 because what if it happens?
No. The thing is, the probability is given by the area, right? So now I'm saying it's just 1 point. Yeah. So that limit tends to 0.
Yeah. So basically,
the area tends to 0 when you take a pick a point. So then that limit means basically the area tends to 0. That means probability is becoming 0 here. So if you like what I said was not the probability at y, the probability up to y. That means I was discussing the case.
Smaller than y.
Yeah, x is smaller than or equal to y. So just want to clarify in case if you got it wrong. Okay, so that is this part. See here it is less than y. So whatever I wrote, everything was correct, but maybe the one sentence was not fully correct. Yeah. So So how do you calculate this? If you have this, then if you have the corresponding CDF, let's say CDS is 5, then the probability will be 5 of y, right? So then here, sorry. Yeah, here I want to calculate this probability, but phi is the CDF associated with the unit variance and zero mean Gaussian distribution. So, but then we have to normalize to that. That's what we were doing here. Shift by mean and divide by the standard deviation. So that will make it a normalized random variable. So then you can calculate the probability here. Then everything is like what we said, so like discussed so far. Yeah. So it's actually simple. I just wanted to clarify that. And yeah, so let's start from this this part. So we were seeing many classes, like so we saw in this course we are discussing convex optimization. So maybe one of the important class that we are studying here is con programs in convex optimization. So whatever we saw so far fits into this framework. And the class especially we were interested is STP, and most of the problem that we are seeing will fit into STP class. Okay, And yeah, so that's what we were discussing. So we skipped one topic called geometric program. So I just wanted to complete this hierarchy. That's why I skipped that. But geometric program will not fit into this program. Maybe you can bring that into this framework, but in its original form, geometric program is not convex. We'll see that. But using some simple transformation, we are bringing that to a convex framework. So let's see what is a geometric programming. Yes, so this was the topic that we skipped. Yeah, so geometric programming. So let's say, yeah, before going to GP, let's see what is a monomial function. So monomial function is a function of this form. F of x equal to, so x is a vector here with x1, x2, and xn as the component. So you can form a monomial function like this. C into first component raised to a power a1. So here the thing is, the way monomial function is defined is like this. Uh, x can take only positive values. Each xi can take only positive values. And this guy here, the coefficient has to be positive. But the exponent can be any real number. So I can write an exponent like this, or an exponent like this, -2 or -10. That is possible in the monomial function. So then this is different from the polynomial definition, right? Where we were not allowed to have something like this, a fractional exponent. Yeah, so this is a specific function uh, called monomial function. Uh, and uh, so then there is another function called polynomial, which is you have several monomial function, many function like this, and you are summing all those individual monomial functions. So everything, all these constraints are applicable here also. That means domain has to be positive, and this guy has to be, this guy is also positive, the constant, right? And AI can take any value. Now, how do you, is this, if you have this in your objective, is this a convex function? You are multiplying the component, which is not a convex function. You can just verify this using the basic definition of convexity. So this is not a convex function. Then how do you deal with this? It's very simple. You can think about it now itself, and the moment you look this, you will get some idea. So you have something, you have many things which are multiplied together. Since it's a multiplication, it's not convex. Now you want to take it convex. If it was an addition, it would be convex. So what you have to do? Which operation you have to do?
We can connect it.
Logarithm. That's it. So just take the logarithm. So yeah. So what we have to do is, yeah. Before that, let me just formally define the geometry program. It's a optimization problem where you are minimizing a function of 0x. And what is the nature of f0x? F0 is f0 and f5. Okay, all these functions are, that means objective, and the functions associated with the inequalities are polynomial. They will be having this form, and then you have a normal equality. But here the thing is, usually we write 0 here, right? Fix is less than 0, right? Here uh, in GP it is 1, because it doesn't make 0 if you put here. That means Fix is less than or equal to 0, but Fix cannot be negative, because we assume here that for this particular definition of monomial function, we assume that Ci is positive and x's are also positive, so then that cannot be negative. So if you are putting, if you make 0 here, then that is not feasible. You don't find a single point that satisfies this. So the way this is defined is we just put a 1 there. Okay, so you want this to be constant. So this is called a GP. Now to make it convex, what we do is we take logarithm. So it's simple. You have this original function. For example, in a monomial case, it's not a polynomial. Monomial, you just have one term. And in that case, when you take logarithm, you will have log c here, and then corresponding to this a1 log x, like that, right? So this term you can write as a vector a transpose, right? So these are a's are multiplied with a log xi, right? So it is like a transpose into this vector log x, right? So then I'm calling this vector as y, and this vector as a transpose. Then it is just like let me call this as b. So it is less just b plus a transpose y. This is an affine function in y. So now we do the optimization in y, and now everything is normal. So if a problem which was not convex in its original form, now using a simple transformation, we made it into a convex framework. Yeah, so what happens? So this was the example for a monomial function. What will happen when it is a polynomial? Like you have a sum of things. So again, the same thing. You just take the logarithm. So yeah, maybe here we have a1 log x1, right? So so now only difference is this time I'm putting as an exponent, power of e, right? So here you have that, and now if you observe this function we have seen before long back. What is this? Log of sum of exponent. We saw log sum exponent, right? Log sum exponential function. Yeah, so you may revise that. So we proved that while we were discussing that it is a convex function. So this is also convex. Everything is convex. Yeah, so when you take logarithm, this log 1 will be 0. Yeah, so that's it. It's very simple. Let's not uh, uh, discuss further because it's very simple. Just take logarithm, then you have a convex function and a convex problem. So one example, we'll just go through this quickly, not in detail, because it has many constraints and criteria from mechanics, so which I don't want to discuss. Uh, yeah, so this is a cantilever problem where let's say this is the wall and you have a cantilever. Basically, I think it's like you have several pieces here. So this piece is smaller than the first one. In it has a small volume, right? So the problem is like you are applying a specific f, and you want to minimize the deflection so that it will hang or something. So let's not go into detail, but only thing what I want to say is, yeah, so here the problem is, so minimize the total weight of this guy. So you cannot make it very small, then it will deflect a lot. So minimize the total weight. You have to keep a certain dimension for a, right? Certain width, height and length. So minimize this, uh, but it has to satisfy certain criteria. Like for example, the stress cannot be more than a specific value, like that. So basically, yeah, let's not go into detail, but only thing I want to say that here, if you see the objective function and constraints, they are like this. So for example, total weight is this is the width and height of each block, and we are assuming that each blocks are having unit length. So what will be the volume? W into H1 into 1, since it is unit length. Now that's a volume. So if you multiply that with the density, you will get total weight. So you can discard the density because density will be same in all the blocks, right? So we are assuming that we are constructing the cantilever with the same material. We do not change material from here to here. So that will also be, the density will be constant. So you can say that the weight will be in this form, and that you are minimizing. So this can be thought like a what polynomial function, where now we have the power to be 1. And but important thing is there are many other constraints which have negative power. H1 is -2, something like that. So altogether, if you formulate the function, you have the objective here, which is a polynomial, and you have several constraints here which also fit into this GP framework. Now you take the logarithm and solve the problem. That's it. So let's not you can skip this because this, you don't need to go into details to see what it is. But the only thing is, in any problem, uh, if you come across sometimes like a multiplication x1 x2 x3, or x1 raised to -2 x2 raised to -3, then you should think about taking logarithm and bringing that into an optimization framework, that is GP. Yeah, so there is one more example. Again, I will skip this because this is not important.
So the reason you can just solve the log of the problem is because the log function is always increasing.
Yes, that's a very important point.
Yeah.
So because you are minimizing something, now instead of that, you are minimizing log of that. So this is only possible when because that is monotonic. Yeah, right. So it could be the other way also. It can be decreasing also. Then we have to flip the sign or something. Instead of minimizing, maybe you can go for maximizing. But it has to preserve this monotonicity.
Yeah.
So since log is a nice function, which has this property, when x increases, log x increases, then we can instead of minimizing x, we can minimize log x. This, and I will skip the next example. Yeah. Because I don't think you will come across any application for this this minimizing spectral radius of non-negative matrix. Let's skip that. Yeah. And now we move to the last section. Yeah, again, this was the class hierarchy of classes we saw, but GP will not fit in here. Only after maybe taking the logarithm, that we can fit here. So if you, but the conclusion of the discussion so far was, if you have a problem like a which fits in this area, then that is easily solvable. Okay, either the solution solvers are there available, or we can come up with some algorithms to solve that. So in the coming sections, you will be seeing, after duality, you will be seeing the many iterative algorithm to solve gradient descent, this kind of technique to solve this. Okay, so yeah, sometimes you will come up with an iterative algorithm. Sometimes you can directly use solver, but it's not like you have a problem and okay, I have a problem. There is a solver. Just match the form and solve it. You should understand the theory so far. What is the function and how can you solve it? The other thing anyone can solve, right? Just to match the framework and put in feed that to your solver. That anyone, you don't need to learn optimization to do that much, right? But yeah, so the thing is, it's not only just using a solver. You have to understand the theory that we are discussing. So by today, you will be finishing a major part of the theory, and then one more section, duality, which is also very important. That will be coming in the lectures. I think Emil is taking that. Yeah, so let's move forward. Now the last topic is vector optimization. So, so far we were discussing the case of scalar objective functions. So what is a vector optimization? A general vector optimization is minimize a function. Now f is not a scalar function. F is mapping from Rn to uh, so far what we were seeing was f maps from Rn to R. Now it is mapping from Rn to maybe Q. Yeah, Q, RQ. So this guy here is not a single value. It's not on a real line. It is a vector now. Okay. So now how can you minimize this? That's a question. So then the moment we say that, then it is about comparing two vectors, right? So it is not easy. It's not straightforward. It's like how do you compare two convex number, 2 plus 3i and 3 plus 1i. So which is bigger or larger? You cannot compare straightly, right? Maybe you can say that one is having larger amplitude, or one is having like more one is bigger in phase, right? But you cannot compare these two. But we saw a concept called generalized inequality to compare vectors, right? So that will play a role here. Yeah, so this is the general framework of a vector optimization problem. It is the same, only thing now is this guy here is a vector. Yeah, so then what is a convex optimization problem? Same thing, but now f0 has to be all the functions involving have to be convex, right? So this is convex. All fi's are convex as usual, but now f0 is a vector. So how do you define the convexity of a vector valued function? Only through a generalized inequality. So you can say that f0 is k convex. So you are defining the convexity using a generalized inequality on a cone, a proper cone K. So we already saw what is a K convexity. It's just the definition of the convex. The Jensen's inequality will be like very similar. Only thing is you use instead of the normal inequality, you use a general inequality and associate that with a which is associated with a cone, right? Cone K. So in that case, you say that the function is convex, but now this is a you are comparing vectors, so I can do only that with the help of a cone. So I say that it is K convex. That's what this is. So if you have everything convex, then the problem is a convex vector valued optimization problem. Now what is the issue with this? We already saw this. What is the issue with a function which maps from a vector to vector, an objective function? Okay. So what we have seen so far is this function maps from a vector to a real number. Then it is very nice. We are happy with that. Then why we are happy? Because in that case there exists a linear order. So if you have two number or many number, 2, 3, 10, you can form an inequality. You can order that in a line, right? You can you can say that one is greater or lesser than the other one. So this will not happen in vector function. So for vector optimization, minimization is with respect to a proper cone, right? So, but then the problem is generalized inequality is not a linear ordering. So it can happen that we have two vectors. We cannot say one is bigger or larger. Why? This we already saw. So how do you make an inequality with respect to a cone? Here I'm showing an example. So let's say that we are using this cone in our optimization problem. Okay. and this is our feasible region. Our variables can take only values from this region. Now, when do you say that y vector y is greater than vector x? Only when y minus x is greater than or equal to. So this greater inequality has to be defined with respect to this cone. Okay, so you can say that a vector y is greater than x only when y minus x is y minus x belongs to this proper cone. Okay, or in other ways, other words, we can write that y minus x is greater than or equal to 0 with respect to this proper cone. Okay, one thing is I'm just writing this here. This is just the inequality. It doesn't mean that y and x has to be in this cone. It can be anybody. X can be here. Of course, y in this case, y and x cannot be here because our feasible region is this. So it has to be here, right? Yeah. So yeah, just don't. I just wrote the inequality here. That's all. It doesn't mean the positions on x and y with respect to cone. Yeah, so let's but what is the real problem here? Let's take two vector x and y, and it can happen that when you take y minus x, that point is here. Okay, and x minus y, that point is here. It can happen this. Okay, I don't know, in this is not these y minus x and x minus y are not specific to this point. I'm just taking these points. So in this case, y minus x doesn't belongs to the cone. X minus y also doesn't belong to cone, this cone, right? So this is not happening, and also x minus y is not belongs to this cone. So it can happen that both of this inequality, y is less than or equal to k, or x is less than or equal to y, both are false. So this is a major problem here. Okay, got it?
It just can happen.
It just can happen. I'm saying an example.
It depends
Okay?
on how big the cone is.
My point is, this is not a linear order. Always you cannot say that y is less than x or x is less than y. There can be situation. That's why I'm writing here. It can happen that you cannot compare these two. You cannot say one is bigger or smaller than the other. Okay, so this is a major problem here. This was not in our traditional optimization problem that we were discussing so far, which involve only scalar objective functions. Yeah, so how do you deal with this situation? So now we will come up with the optimality of such vector valued objective function. For that, we use two concepts. We define optimality using either optimal point or Pareto optimal point. Let's see what it is. To establish this theory, first I am forming a set O, which is the set of objective function. Okay, the values of objective function for all feasible x. That means, let's consider an example in R2. So my f0 is objective function is, let's take this example. It is mapping from R2 to R2. So let's take this as the feasible region. So x has two components, x1 and x2, and any point of in this region is feasible. Now what is my f0 is doing? Mapping that to again to an R2, and let's say each point I'm mapping from x, the feasible region, and I'm getting values, right? Objective values for that. So I call this set as set O. What is the set? It is a set of achievable objective value. Of course, if you have an x here, it may point somewhere here, but that is not achievable because that x here is not feasible. Okay. So this is the set of achievable objective value, which I call as set O. Okay. Now optimality is defined with respect to the minimum and minimal of this set. So we saw two concepts while we were discussing convex set: minimum of a set and minimal of a set. Okay, so that concept we will use here. So we will use that one. Yeah. So here I am just representing as the first component of this is okay. Yeah. So I call f0 x as f0 x1 and 2. This means the first component, and this is second component. Like how do you say x1? Okay. Just a notation I'm using. Maybe you can use f0 1 of x. That's also. Yeah. So now, yeah. So the point is now we discuss the optimality with respect to this set. Or how do you say a point x is optimum? So for that, x is optimum. No, you cannot go like directly to a local minimum, because the problem is here. What we are discussing here is a vector valued objective function. So it can happen that 2 points cannot be compared. Okay. So how do you deal with that aspect? That's what we are discussing. So x is optimum. A point is optimum if f0x is the minimum value of the set O. So you have a set here. So what is the minimum value? Let's say in this case minimum doesn't exist, but let's assume that this point at this point f0x is the minimum, and this is the minimum of this set O. Then we call that f0x is the optimum value, and the corresponding x is the optimum point. So x is optimum when f0x is the minimum value of set O. So what is the minimum value? This we already saw. We have a set O, and we say that f0x is minimum of the set O. Of course, you can say this only with respect to a generalized inequality, because this guy is a vector. You are comparing vector. You are talking something about the minimality of a vector. So then you have to bring a cone, okay, a generalized inequality. So you can say that f0x is minimum only if for all y's, all f0 y's belonging to the set O, f0x has to be less than or equal to f0y with respect to the cone. That means here, if you pick a point and you are saying that this is optimum, then all other point has to be less than this point with respect to our cone, original cone. Okay. This is a wrong figure to discuss the minimum, because there is no minimum in this. We will see this. We have already seen this. Okay, but I will discuss. Yeah. So this is the case. You have to pick. For example, this is our O. Then you have to consider all the points, and this point, the minimum point, has to be less than all other points with respect to the cone. That's what we are saying. So in other words, how can you see this? This we already saw. So what you have to do is you have to shift the point. You have to form a, not shifting, form a new set f0x plus k, and check whether that the original set O belongs to that f0x plus k. So let's take this example. It will be clear. We saw this already. So we have, let's consider this proper cone here. It is R2 plus. That's a cone, right? So R2 plus is our cone. So what is the minimum of this set? It will be this guy. Why? Because if you take any vector here, that will be less than f0x with respect to R2 plus. How do you say this? So just pick this guy. Just see what sorry. Just see what it is. It will be all the region here. Okay. That means f0x plus this cone. That will be this region. Now my point is whether O is contained within that region. right? It is inside that, this f0 plus k, right? O is fully inside that. Okay, but if you pick a point here, it is not minimum. Why? Because in that case, f0 plus k is this region, then O is not fully within that region. Okay, within that set. So this is not an optimum point. In other words, or minimum points. So in other ways, if you pick this, then you can prove that f0x is less than this point with respect to this con. So that cannot be happen. If it should not happen if you say that f0x is a minimum. So this is minimum. That means it's lesser than all other guys in the set. Now you can see that minimum is it is not that minimum is unique. Only one minimum can happen. Yeah. So yeah. So this we already saw, but this is very important concept. Now what happens? Let's take this set. What is the minimum of this? Which one? This one?
Depends on the components.
This one? Sorry.
Does it depend on the cone? Oh, wait.
So let's take this R2. Yes, that depends on the cone. But you can see that minimum doesn't exist here. Let's take R2 plus.
Because it will not be.
So you will not be able to, for example, if you pick this point, then this region, then you have to form this region, right? Since you are taking R2 plus as your point. So the original set O is not within this region. So that means there is no minimum. So you cannot find any point where F plus K fully contain the original set. So there is no minimum here. So it is, this will not always happen. You cannot always find a minimum. That's a point. Yeah. So the thing is, everything was convex, right? We had a convex problem, but since there was an inequality, uh, or the function was a vector valued function, so we have to use a con to compare the values. So in that case, though the problem was convex, it can happen that there is no minimum.
So finding minimum value, we have to first draw the cone and we have to see the.
So this is no, you cannot draw the cone in a particular way. So this is the like picture what is going on there. Okay. Of course, this is just a simple example in R2. If, for example, you have R100, what you will do? You cannot draw or something, right? So yeah. So we'll see how are we dealing with, or we pick R plus because it is easy to draw. Like if you pick, for example, positive PST cone, then it's not easy to draw, right?
Is R2 is a cone? No, just R2 plus is a cone. Just take a different entire two dimension.
R2 is a cone, but it's not a proper cone. We are talking about, to make a generalized inequality, the cone has to be proper cone. But if you consider when there are two, then x is a point, minus x is also a point in that. That means that set is not pointed. So for a cone to be proper, it has to be pointed. Then only you can define an inequality with in association with that cone. Yeah. So we should not take R2 here, only R2 plus. Yeah. Now what we'll do is, what we'll do if we don't have a minimum, then you have to move for minimal point. Then we have this concept of Pareto optimum. It is like, roughly speaking, like almost optimal. Okay? Roughly optimal, something like that. Okay, which is defined using the concept of minimal. Okay, so what is a minimal? Again, we will revise this. F0x is a minimal offset O with respect to a cone. Okay, inequality defined with respect to a cone. That which implies F0y belongs like for some F0y in O. If you say this, F0y is less than or equal to F0x, it can only happen when both are equal. So what I'm saying is F0x is minimal. Then if you are saying that, okay, I have an F0y which is less than that minimal value, this can only happen when they are equal. This may seem similar to the previous one, but this is different. In previous one, if you pick a value here, and if you're saying that is the minimum, then for all other points, this point, the minimum point has to be less than that, less than or equal to that. But this is not the case here. We'll see with an example. Yeah. So, for example, here, let's consider this example. I have a set here for, and I am marking some point here for, yeah. So what happened if you pick this point? Is this point minimum? First, let's see what is minimum here. Is this point minimum? This point minimum? No, right? Because if you form this region, that is not containing the original set, fully containing. Is this point minimum? No. Is this point minimum? No. Okay, so minimum doesn't exist in this way. So now what I want to do is, I will ask a question. Can you compare this point? Can you compare this point? We have a vector half half and another vector 0 1. Okay, this point and this point. Can you compare these two vector using R2 plus? That's our code. Okay, so here I am considering K equal to R2 plus. Can you compare this point? So let's call this guy as X and this guy as Y. So what is X minus Y here?
Minus
X minus Y, yeah, minus half plus half, right? So that is that in R2 plus or cone? R2 plus means this region, right? R2 plus is this region. So since this has a negative component, it is not a part of part of the cone. So we cannot say that then X is not greater than, I will use this notation, not greater than or equal to Y with respect to our cone K, which is R2 plus here. Now just take Y minus X here. What is this?
The same thing, but with the minus in the second.
Yeah, half minus half, right? Again, this is not in R2 plus, so you cannot say that X is less than or equal to Y here. So that means if you are considering this point, you cannot make a comparison with this point, right? So in other words, if you draw a line like this, sorry,
But if the cone would have been absolute X, for example.
cone is absolute X.
Yeah, or the
What is absolute X is not a cone, right? Okay, so you mean all the values inside, right? Yeah, that's a cone. Yeah, in that case,
then 1.0 would be the minimum. So if that would have been the cone. because from 1 to 0 to 0 to 1.
Mhm.
But you can only.
So
have
what you are saying is now your cone is this guy.
It is just rotated.
Yeah. Then this is minimum or not 1 0.
Yeah, that would be the minimum.
How? Because when you shift,
cannot shift it to anywhere else and have the whole set.
no,
within-
when you shift again that will not contain the under set, right? So you can have points which you cannot come there. So you are talking about the minimum, right? The minimum, right? It can happen only when you can compare all the points. So why there is no minimum here? Why there is no minimum here? Because for this point you cannot take this region into comparison. Okay. So minimum exists only like this situation where this point is comparable with all other points in the set. Okay. So you sorry.
But if the cone would have been not R plus, but like a bit rotated, then we would have the same thing.
It depends on the set, right? So it depends on the shape of the set. So if that was the case, if you bring this region, so here we were forming a region like this to check that. In your case, it will be something like this, right? So then also it's not containing, right? So you cannot say.
But if you bring it to 1.0,
Yeah, 1.0 it can happen, but depends on the shape. Like if your cone is like this, yes, that's a minimum.
absolute X. So
Yeah,
that is
yeah.
45
Yeah,
degrees.
yeah. So this has to be like then slope +1 and -1. Okay, and but if your function was cone was something like this, no. Okay, so that's why I said it depends on the shape.
Okay, so why did you pick on R2 R plus?
This is just an example to show you what is concept. Okay, you can pick any cone. So R2 plus is easy to visualize. That's why we are picking that.
No, I understand, but it is not something that is part of your problem, or it should be specified in your optimization problem.
What I didn't get your point.
Like normally, you cannot freely pick your cone. I think. Of course, you do it for the sake of an example.
Yeah.
But if you get a problem, you can, it will be defined. You can just say,
but
let me take this cone.
This R2 plus is normally we use that because we want when you do comparison we want component wise or something. So this is a very often used cone. This cone and PS2 cone for matrices. Okay. Yeah, but of course
because I didn't see the cone specified earlier, and you just write, oh yeah, let's take R2.
Yeah,
and then
this
I think,
here.
Okay, you just
Yeah,
you have to take into account.
Each entirely, I agree. It entirely depends on the cone and the set. Okay, so for a specific set O, if you pick a different cone, then it can happen that minimum exit or the minimum vanishes. There is no minimum.
So it's not like for the sake of solving the problem to find the minimum point, we can take anything.
No, you cannot take any.
It's like it will be like with the problem, like the cone will be like this.
Yeah, and the point is minimum will not exist in many cases. So we will see what in that case what we'll see. Yeah, correct. Yeah. So what I was saying is, in this case, if you pick this, why this is not minimum? For minimum, all other points has to be in the set has to be comparable. So we just saw that this point is not comparable, and all the points here and also here, these are not comparable. Okay, you cannot compare those regions. So in that case, you cannot say minimum because you cannot compare. Then how can you say this point is minimum? In that case, you can say that this is an optimal or Pareto optimal point. because how do you define Pareto optimal point? This point is Pareto optimal point. That means if you can say, so this is a bit tricky. A point f0x is a minimal point, or in our case, we just call it as Pareto optimum. F0x is a minimal point. That means if you're saying that f0y is less than f0x, that means it can happen only when both are equal. It doesn't says that this should happen for all y in O, right? So so maybe I will specify here for some or for any. If you pick any y from O, and then if you are saying that this is happening, that can happen, this inequality, you are saying that my x0y is less than the optimal point. It can happen only when both are equal. That means this doesn't have to satisfy for all the points here. But if you pick any point which are comparable, then if you say that that is less than this point, it can happen only when that point is equal to this point. Okay. In other words, uh, an easy way to visualize this is just form this region x0 x minus k. So in our case, it will be this guy here, and take the intersection of that with the original set O. So we take the intersection of this region and the original set O. What will be the intersection? Just that point. Okay. This is the way to visualize that. So let's see again. This is an important concept. Let's see again this set. So what will be the first question is, does O2, so this is O2, my O2 here, does O2 has an optimal point?
In the middle of the O?
No, it's not.
No, it doesn't.
It's not.
Okay, I was not.
With respect to R2 plus, right?
Yes. I was not asking. Yeah, so optimal point means, yeah, correct. What is this? What I'm asking, whether it has a minimum.
Yeah.
Okay. Optimal means the optimal. That means minimum.
Yeah.
Okay. Now, minimal, it can have minimal. Let me write this. It may confuse you. At least it's confusing me at some part. So you say that optimal point exists, then that means there is the minimum. This is okay. But in case the minimum is not there, it doesn't exist, and you only have a minimal. This is this guy here. Okay. In that case, we say this as, this is now not optimal. This is Pareto optimal. Okay. Yeah. So my question is,
this is only defined like this for vectors. Eh? This doesn't exist for cubes one.
exists for what? Real line. Real
Yeah,
problem. Yeah. In that case, everything is same. So you don't
the minimal.
yeah.
The minimal.
Yes. Yeah. So thus O2 has an optimal point. So I'm asking whether the set O2 has a minimum. Not the minimum, means it's unique. So minimum is always unique. So before moving to this example, let's ask another question. Whether, so we just saw that this point is a minimal point. Does it has another minimal point? Minimal point. So any point on this line is a minimal point. If you pick this, that's a minimal. If you pick this point, that is again a minimal. Okay, so you have to draw this. Sorry. So this was minimal, and this was also minimal, because if you take the intersection of this and this, you will get this set. Right? So minimal is not unique. Yeah. Now come back to our discussion. does O2 has an optimal point or the minimum? No, right? Because if you take any point, you will not get a region which fully contain the set O, right? So it doesn't. So answer is no. Now find the Pareto optimal points here. That is, what is Pareto optimal points? They are the minimal, right? Minimal points. So
That will be like tangent, like touching
tangent,
something.
it has some connection with tangent.
Which is like touching the part
So,
of it.
so if you pick a point here, maybe here, okay, and if you draw this line, if you form this region, okay, sorry, and take the intersection, then that's this point, right? And if you consider this point and take the intersection, that is this point. It will continue maybe up to this point. Take the intersection, that is this point, okay? But what happens if you consider this point? Then the set is this, intersection is not this point. There are a lot of points within that set. So here, in this case, the Pareto optimal point will be all the points up to here in this region, okay? So in other ways, you can just see, since our cone is R2, just draw a vertical line, bring that here and find the point where it is touching here. A horizontal line, bring that here and find the point where it is touching here, and all the points within that. So what is this, these two lines, two tangents, that we'll see soon. Yeah, so this was the this was our discussion. So what we saw that in a vector valued problem, it is difficult to minimize because inequality can be the linear order does not exist there. In that case, uh, if the minimum exists, then we will pick minimum, means minimum of the set of all achievable points. You from the point you just form the set of all achievable points, and if the minimum exists, then that is the optimal point. If it does not exist, then you can think about a Pareto optimal point, which is these points, which are these points, okay? Okay, so let's take a break here. So let's start. So what we saw was the problem involving vector valued objective function. In that case, um, so there are two concepts, optimal and Pareto optimal, right? So if this set of achievable objective value has a minimum, then we can talk about the optimal point.
Sorry. We just need to check, but it's fine.
Yeah. So in other case, if it doesn't have a minimum, but a minimal value, then you can talk only about a minimal value of the set of achievable function. In that case, it's a Pareto optimal point. It is like saying roughly optimal or almost optimal. So let's see an example here. Yeah, before that, there is a terminology called multi-criterion optimization. It is the same thing. Only thing is the cone has to be R plus. So whatever we discussed so far fit into multi-criterion optimization problem. Okay. So it's a vector valued function, vector valued objective function, and then you have an optimization problem, and this is called multi-criterion optimization when the cone is non-negative orthant. Yeah, so in this case, yeah, of course, then if you are using this cone, then it's like a component-wise comparison, right? Component-wise comparison that we already saw many times. So roughly speaking, we want all the individual functions. So f is the objective function and it has individual, right? It's a vector, right? So individual components. Let's call this guy as first component as f1, f2, like that up to fq. So roughly speaking, if you are minimizing with respect to r plus, what you want to minimize is you want to minimize each component, roughly speaking, because let's say we have a problem with you are investing in a stock and you want to what will be the, in that case you want to minimize uh, okay, no, maximize the return. So that means you have to minimize the negative of return and then you have variance or risk in this case. Okay, so let's call this as f1 and let this be f2 or something. So you have two criteria. So what you want to do is you should get maximum return or minimum minus return, and at the same time minimum risk, right? That you should be able to find such a stock to invest. That's what you prefer, right? So in this case, you want to find some stock which is minimum in both of these, but it may not be true in practice. One which is expected to give maximum return can have more risk, right? So that's why we are saying roughly speaking. Yeah. So there is nothing new in multi-criterion optimization. It's the same problem with RQ plus as the core. So the same discussions here. X star is optimal when y is feasible, and we can write this for all y's. Okay, means this is the minimum. And here, this is the concept of minimal. Okay, so when we say that a point XPO is Pareto optimal, when that the point associated, the objective value associated with that point is the minimal or a minimal. Okay, so this is the same discussion that we saw just before. Yeah, so now there is a trade-off between objectives. Let's say in a problem we don't have minimum and only we have Pareto optimal. So there are a lot of points, right? So in that case, it's like different points. One stock means low moderate return and moderate risk, and other stock means high return and low risk, something like that, right? No, high return means of course it has to be high risk, right? Generally.
The example of stocks is a bit, well, that's really easy to convert to one number, value in money. This is how, but what you have is like each stock is one of the vector elements, basically.
Yes.
Yeah.
What I'm saying is corresponding to each stock, you have a return, and that also have a risk, right? So,
so that's the two variables.
Yeah, two variables.
Okay, so
right?
like
Yeah.
this.
So let's take an example. Let's keep this economics and come back to signal processing. That is easy for us. So yeah, let's take an example. A regularized least square. So least square is this guy. Find the value of x that minimize this, which we saw the cost form expression for this using a pseudo inverse. Now I want to regularize this, minimize this, and also the norm of x. So this sort of problem often comes in our research, where, for example, you are minimizing and you just put a norm, L1 norm, L0 norm here. That means you are forcing sparsity in X. Okay, let's not go into that direction. But what I want to say that is this sort of things are coming. So here I put a plus unknowingly, but yeah. So here what at this point we are not adding. We will come to that soon. But it is like you have two values and vector of two values, you have to minimize this with respect to R2 plus. So if you plot this, so I'm plotting x2 norm of x2 square and x minus b square, basically this for all, and then for all feasible x, then you will get this region. Okay, so this is our set of achievable objective function. So what is happening?
Yeah.
Yeah. So in this case, is there any minimum? No, right? There is no optimal point for this problem. But we know why, because we cannot make something, a region like this which fully contain all, right? But you know that at all this region, you can follow the discussions of our Pareto optimal point. So that means this is the Pareto optimal point. So now how do you choose a point here? So if you pick a point here, right, then that case you will have a particular x2 corresponding to this point. You will have a particular value for the first term and a particular value for the second term. If you pick a point here, again you will have a particular value for this term and a particular value for this term. So this is like these are different solutions, right? How do you pick a solution? That depends on your
Whatever you feel like.
Yeah, so it depends on your requirement or like nature of your problem, or what you want to do, something like that's why we are saying that if there are multiple Pareto optimum value, there is a trade-off between the objective. Okay, so you have to choose whether you should. Sometimes you want to, for example, in this problem, sometimes you want to give more importance to sparsity, then you should move towards to uh, this part. Means you should give more importance in minimizing this part. Okay, so then you will pick a point where this is minimum. Okay, that means you will pick this point. Okay, but if you just want to discard this and pick this guy, minimum value of this, then you will move to this direction. Okay. Yeah, yeah. So this is an example. Now let's move. There is a problem from finance. Let's discuss. Let's not discuss, or discuss at the end. But it is the same thing what I was saying. These are the fraction of stocks that you are buying. So this is the minus of return. You want to minimize that. Okay, and this is the risk, which is basically associated with the variance. Yeah. So like that's let's skip that. Now let's move to the very last topic, scalarization. So now what we so far what we were seeing is the f0x was a vector valued function. I will denote it as f01. Okay, later before I was using this notation, I think 1 or something, but let's pick this. Sorry for the different notation. f02x. Okay, so you have this function. Now what the problem, why we were facing problem, because this guy was a vector. Okay, so the simplest question what I can ask is, can I just add this and make a scalar? So what I do is I just add f0 plus f1 plus f2 like this. Okay, and just minimize this. That's the question. Okay, but again, so can you go more general? Here I am giving equal importance to all. So can I just multiply with a scalar lambda 1, lambda 2, lambda 3? And for example, if you want to give more importance to f2, okay, so this should be 1. Yeah. If you want to give more importance to f2 in your optimization problem, sorry, f3 in your optimization problem, then you have to make lambda high, like how we saw that. Okay, like here, for example, I want to give more importance to sparsity. So when I add this together, what I do is I pick a large, I give a large weight to this term. Okay. Yep. So this technique is called scalarization, but there is a theory behind that. How do you pick the scalars? That's the point. So for that, yeah, so before going to theory, just let's state what is happening here. Yeah, so X is optimal for a scalar problem. So now what we are having is not this guy, the scalar version of this. That is what written here, lambda transpose into F0x. Okay. So now this is a new problem, which is a scalar version of the original problem. This is not the same problem, of course. It's not same. It's a new problem, and uh, X is optimal for this scalar form. So if you find, now this is easy. This is our standard convex optimization problem. And if you find an optimal point for that, then that will be a Pareto optimal for the original vector problem. Okay, that's the theorem here. So how? For that, you have to again revise your theory of dual cone, right? So what was a, let's see, quickly go through the background. Uh, so we saw what was a dual cone long back, maybe 6 lectures back or something. So let's say we have a cone K. What is the dual cone? Dual cone is K star such that it is a set Y such that you pick X from the set, from the cone K and make an inner product with Y. Then if you if that inner product is greater than or equal to 0, in that case, the Y is part of an element of the dual cone. Okay, so collect all those Y's and you will get the dual cone. That's the dual cone. And some interesting fact is dual cone is always convex, even though K is not. Okay, this you can prove from the definition itself because this is just an affine function. You can prove that easily. And now let's see some example. Let's see some geometric interpretation. So what I'm saying is, geometrically, a vector y belongs to dual cone if and only if minus y is the normal of a hyperplane that support k at the origin. So the moment you see this, so what is this hyperplane? It is a hyperplane passing through origin. Okay. So now you are doing something like this. That means that's a half space. Okay, there is a hyperplane at 0 and then a half space at one side of the hyperplane, right? So keep that in mind. Now let's see what is happening here. Let's take this cone, the green cone here. Okay, that I'm calling as K. So what I want to do is let's pick this guy X transpose Y equal to 0. Okay, first let's pick a Y here, or I just take a vector lambda 1 from this cone K. Okay, so now I want to find this equation. Okay, that is a hyperplane passing through origin. So this is the origin here. Okay, origin. So the cone is this, and it contains this is the origin. So now what will be that hyperplane? That will be this guy here. Okay, and now what I'm saying is that is less than or equal to 0, or in our case it was greater than or equal to 0. Sorry. Okay, so that means you are saying that it is this region. Okay, remember that was for this particular vector. Now you pick another vector lambda 2, okay, and do the same logic. Then you have this plane here, and this inequality means this side of this. So these are the extreme vectors I picked from the boundary of the cone. So if you take intersection of all, then what you will be getting is this cone. That is the dual of this cone. Okay. Basically, what you have to do is go to this extreme boundary and make a 90-degree. Okay. And go to this guy, make a 90-degree, and form a cone with that. Okay. So what will be a dual cone of Rn plus? Go to this guy boundary, 90-degree with that. This guy 90-degree. So that will be the same guy itself. So K star in this case, K star equal to K. So this is self-dual. Another example is your SN plus. You can go to textbook for the proof of this. It's not usually easy to show through a picture. Yeah, so some properties of dual cone. Why we are saying this? Because this is required to prove this statement what we made here, which says that if you have an optimal point for the scalar problem, then that will be the parietal optimal point of the original vector problem. Yeah. So some properties. This is from the textbook, our textbook. So K is convex, even if K is not convex. So there are other properties, you can read it, but also K is a proper cone. Then the dual cone is also a proper cone. These are two important properties. Now, so then what we are seeing is K is a so we have a cone K, which is a proper cone, and then a K star, it's dual, that is also a proper cone. That means you can associate an inequality with any of this, right? So that is a relation between. So we call, for example, if you pick this inequality with respect to K, then the dual of that inequality is defined using dual of that cone. Okay, simple. So this is an inequality. The dual of this inequality is the same guy with the K replaced with K star. Now the important properties or very interesting property here is, let's say X is less than Y with respect to K. Okay, so in our normal in our real valued function or a scalar function context, if I say 2 is less than 3, okay, then I can multiply both sides with a positive number, right? Then the inequality still holds, right? Here also we can do that. So what I'm saying is X is less than Y. Now what I do is I multiply, or here in this context, it's an inner product. I make an inner product with lambda, then the inequality holds for all lambdas. This we can say when you pick lambda from, when you pick positive lambda, here I have to pick a positive number to preserve the inequality. But here you have to pick a positive lambda, positive in the sense positive or equal to 0. It's a non-negative lambda in this dual cone. Okay, so an inequality in a cone K can be transformed to this inequality only if in that case lambda has to be from the dual cone. So this is an important property. Now we'll come to the proof. So what we had initially was a vector optimization problem where we were minimizing with respect to K, and this is a vector value function. Now what we do is we make a scalar optimization problem where we convert this into scalar. It's a weighted sum of each component. Of course, lambda has to be greater than or equal to 0 with respect to K star for this theorem to happen, right? Because we are using this inequality. Now, what the original theorem was, X is an optimal of this problem, then we can say that it is a Pareto optimal for the vector problem. Okay, this is what we are going to prove. It's simple. assume that X is optimal for P2. So I call this problem as P2 and this as P1. Okay. Assume that X is optimal for P2. And then we make a second assumption. X are not Pareto optimal for P1. Okay. So this is, we are going against the theorem. Okay. Now we saw that this will not happen. Okay. This is a rough sketch of the proof. So X is optimal for this, but not Pareto optimal for this. Then, since it's not Pareto optimal, okay, that means that corresponding objective value function x0x is not a minimal element, right? So then there exists a y, a feasible y, which satisfy f0y is less than f0x, and f0y is not equal to f0x. So if this guy has to be a minimal or minimal point, then this will happen only if this is equal to this holds by equality. F0y has to be equality. Okay, this is the definition of basic definition of minimal point, right? So then we can say that f0y is less than or equal to, and f0y is not equal to f0x. There can exist such a y. Okay, what does this mean? From this, I just bring the terms, rearrange the terms, and I write like this. Okay. Now I can multiply with the lambda transpose. Remember, lambda has to be from the proper cone, and still the inequality holds. That's what we saw here. Still the inequality holds, and yeah, basically what I did was, okay, actually we don't need this step. We can directly go from here to here. Okay. Yeah. So we had this, just multiply that with lambda. Okay, you can still get the inequality. And then what is this saying? This is saying that this function or this takes a greater value compared to this. So I think I made a mistake here. Now this is not with respect to cone. Now this is a scalar function. See, here what is happening, you compare two vector. Now pick a vector from its dual cone and multiply with this. These are now scalars. Okay, this is a normal inequality to compare scalar. Yeah, so now what we prove that this scalar is greater than or equal to this scalar, but this is against our assumptions in one, which says that X is optimal for P2. If X is optimal for P2, then this lambda transpose in F0X has to be the minimum of this problem, right? So, but what we saw here is it is not the minimum that can exist. So this contradicts with our assumption. So hence we prove that you can make a scalar version of the original problem, and the scalar has to be this lambda is from the dual cone, and then if you find an optimal point for this scalar function, scalar optimization problem, then that will give you a Pareto optimal point for the original function. And for a convex problem, of course, you can find this is important. You can find you can pick many lambdas and form different optimization problem and get different Pareto optimal points. And if the problem is convex, you can get all the Pareto optimal points.
So this lambda value we can choose randomly.
Yeah, you can choose, and you will see soon in your discussions with the duality more details on this. Now we are roughly stating this idea. So one other thing is yeah, we have to wind up quickly. So let's go for this last example. So it is the same example. So here I'm discussing scalarization for multi-criterion problem. So this is a problem, vector optimization problem with cone equal to R plus, right? R plus R. So what happens there? So it's the same thing what we saw here, nothing new. So earlier we were talking about this guy, vector valued function. Now what I do is I add with a number. Okay, so this is a this is without loss of generality, because you can of course think about a lambda 1
minus here.
yes, lambda 1 and lambda 2 here, and just scale it, right? So gamma will be lambda 2 by lambda 1. Okay, so so now in this case my lambda is 1 plus r. Okay, and yeah, so this is the same plot here, but one important thing is, concept is okay, what we are saying is, so when you find a minimum of this problem, or when you solve this optimization problem, which is now which if it is a convex problem, we can solve it easily. And then what we are saying is, let's say x is the optimum point, then lambda transpose f0 x is less than or equal to lambda transpose f0 y. That means I'm just flipping the sign to make it in the form of a hyperplane. That means at f0 x, this is the equation of a hyperplane which supports the achievable objective function. So at f0 x, we can draw a hyperplane with a slope, not slope, normal to hyperplane will be minus lambda 1 here. Okay. Yeah, so lambda 1 is a particular vector. Okay, you can vary lambda 2, lambda 3. So based on that, you will get different Pareto points here. So here, corresponding to lambda 1, I have this f0 x point. So that means there is a hyperplane like this, which supports the achievable set at this point f0 x. That is what this equation is saying. Okay. Now, like, so maybe you have to see the equation of supporting hyperplane, revise that topic from convex set, right? So there we discussed that in a set, convex set, at a point x0, you can form a hyperplane and which support that set, okay? Then we saw what is equation of that a0 x is less than or equal or greater than or equal to a0 x0, that point. So this is the same guy here. Yeah, so coming to our problem, so let's see what happens here if you pick different lambdas. So lambda is now in this form 1r. So when you make r equal to 1, that means lambda equal to 1 1. Okay, that means the normal is minus lambda here, minus lambda. So in this case, the normal will be minus 1 minus 1. So to find that point, you, so this is something, this is a minus 1 vector. So draw a line, hyperplane, and just see where it is touching here. Okay, so that is this point. So this is the Pareto optimal point corresponding to this lambda. Let's take another example where r equal to 0, a new lambda with r equal to 0. In this case, lambda will be 1 0 and normal will be minus 1 0. So it will be this. Okay. So the hyperplane will be this guy here. So that is touching here. If gamma is very high, infinity, so you can think about, so this is very high infinity. So you can think about that as a 0 1, right? So of course you can write something like 1 by gamma and 1 here. So when gamma equal to infinity, this will be 0. And then in that case, normal will be 0 minus 1. So that will be this guy. So draw a line and see where it is touching this point. So that will be this. So based on the point is based on different value of lambda, right? Lambda, which we use to make the problem scalar, we will have different hyperplane. Minus lambda will give you a hyperplane, and the point that touches the principal region will give you a Pareto optimum point. So this is just the beginning of the discussion.
That will depend on the gamma.
Yeah, gamma is here. here just I wrote lambda as one gamma. Okay, so gamma is just a way to write lambda. So the discussion is about lambda, which you use to make the problem scalar. Based on lambda, you can form different hyperplane which touches your feasible set of achievable objective function. So that gives you the Pareto optimal point. So here you have this guy. So this was the thing that you were saying, draw a tangent before. So that is this. So that tangent that's corresponding to, actually corresponding to, that was a, what we saw there was a hyperplane whose normal was making that problem a scalar problem. Okay. So we'll stop now.
Have to.